This is the video for section 18-3 in accelerated geometry. We are going to be learning for the first time today fundamental trig identities, several of which you should already be familiar with. So our essential question for the day is, how does the Pythagorean theorem apply to trigonometric functions? And if you don't remember the Pythagorean theorem, we've already used it recently in Unit 17, that whole a squared plus b squared equals c squared thing. So how could these possibly relate to the unit circle and to trig functions? Well, we'll talk about them as we get to them. These are your fundamental trig identities, starting with the reciprocal identities, which we're all familiar with. Cosecant of theta is equal to 1 over sine theta. Secant of theta is equal to 1 over cosine theta, and cotangent is equal to 1 over tangent of theta. These two we talked about in Unit 17 when we were starting to talk about the unit circle. Hopefully we realized that tangent of theta is equal to sine of theta over cosine of theta, and cotangent of theta is equal to cosine over sine. So tangent is sine over cosine, cotangent is cosine over sine. Then we get to the Pythagorean identities. And let me sort of explain this to you. On the unit circle, the whole point of it being a unit circle is that theta is down here, the radius is 1, and remember the x-coordinate is cosine, and the y-coordinate is sine. That's the way the unit circle works. So if I was to apply that to the Pythagorean theorem, a squared plus b squared equals c squared, I would have cosine squared plus sine squared equals 1 squared, which is where this first Pythagorean identity comes from. Cosine squared plus sine squared equals 1. That is the most important of the 3 Pythagorean identities. The other two can actually be found by with this first one. If I was, for example, to take everything in this first equation and divide it by cosine squared, so cosine squared over cosine squared is 1. Sine squared over cosine squared would be tangent squared, because remember tangent is sine over cosine. So if they're both squared, then tangent is just squared. And then 1 over cosine squared would be secant squared. So that's where this second Pythagorean identity comes from. What if I did the other scenario of this and divided by sine squared theta? Cosine squared over sine squared would give me cotangent squared. Sine squared over sine squared would give me 1, and then 1 over sine squared would give me cosecant squared. So I tell my students every year that there's really no need to memorize all 3 of these. As long as you have the first one, the most important one, memorized, then you can always come up with the other 2 by dividing the way that I just divided. And then our fourth set of fundamental identities are the negative angle identities. And they say that sine of negative theta is equal to negative sine theta, cosine of negative theta is equal to cosine theta, and tangent of negative theta is equal to negative tangent theta. So notice both sine and tangent change signs, but cosine does not. And then the reciprocals would work the same way. If sine changes signs, then so would cosecant. If cosine does not change, then secant does not change. And if tangent changes, then cotangent would change. Now remember, the whole definition of an identity is that it is a mathematical statement that is true for all values of the variables for which the statement is defined. So what that means is that these identities always work. Cosine squared plus sine squared always equals 1. Tangent always equals sine divided by cosine. All of these always work. So there are usually 2 things to begin with that we do with trig identities. We prove statements that contain trig identities, and we simplify expressions that contain trigonometric ratios in them. So the first thing we're going to start with is proving trig identities, beginning with proving that tangent of theta is equal to secant of theta divided by cosecant of theta. When you are asked to prove a trig identity, this is not like a geometry proof where you have to do your statements and your reasons and your given and all that sort of stuff. You're basically just trying to make one side of the equal sign end up looking like the other side of the equal sign. And when you're trying to decide which side to work with, you want to start usually with the most complicated side, the side that has the most stuff on it. You don't want to touch the other side at all. So for example, here in number 1, the right-hand side of the equal sign contains more stuff. So I'm going to try to simplify it until it turns into tangent of theta. I'm not going to change tangent of theta at all. So I'm going to start with secant and cosecant. 9 times out of 10, the best way to approach one of these identity problems is to try to rewrite everything as much as possible in terms of sine and cosine. So secant, for example, is 1 over cosine theta. And cosecant is 1 over sine theta. So that means that this problem is really 1 over cosine theta times sine of theta over 1. And so now we have sine of theta over cosine of theta, which we know from our trig identities, sine over cosine is tangent. So I have now proven that this secant of theta divided by cosecant of theta is really equal to tangent of theta. Now let's look at number 2 here. Number 2 says 1 minus cotangent theta equals 1 plus cotangent of negative theta. Now as far as proving that one side equals the other, these both are pretty similar statements. But I do notice over here that I have a negative theta, and so that reminds me of my negative angle identities that we have in our list. And cotangent's not in the list, but tangent is. It says that tangent of negative theta is equal to negative tangent of theta. Well, I told you that that's also true for its reciprocal. So if tangent changes signs, cotangent is going to change signs as well. So cotangent of negative theta is really negative cotangent of theta. Bring the 1 down. Look at that. I just proved it. Took me 1 step. Whoop-de-doo. Okay, so I want you to pause the video for a minute, and I want you to try both number 3 and number 4. Decide which side to work with and make it look like the other side. Okay, so in number 3 here, I chose to work with the left-hand side because it had the more terms in it. Sine, really there's nothing to rewrite sine as, but cotangent can be rewritten as cosine of theta divided by sine of theta, which means that my sine values would cancel out, and I would have left cosine equals cosine. So I have proven that. Then over here on the left, there's really not much work to show, but looking at over on the right, the left-hand side of the equal sign, I have a negative angle there again. And so secant's not in my list, but secant is the reciprocal of cosine. And when I go back and look at the list, it says that cosine of negative theta equals cosine of theta. So the sign in front of it doesn't change, but the angle becomes positive. So that means that 1 minus secant of negative theta is the same as 1 minus secant of positive theta. Which, look at that, it looks like all I really did was rewrite it, but I really did prove it. And I want to say, too, that when you're doing these and you're having to simplify them or to prove the identities, you do not have to give a reason for your steps. So you don't have to say by negative angle identity. And over here, you don't have to say by cotangent ratio identity or anything like that. You just have to do the work. So let's try some more. These say to rewrite each expression in terms of cosine of theta and then simplify it. So they're wanting you to simplify, but they're kind of giving you a head start. They're wanting you to use the fundamental trig identities, which are things involving sine and cosine, in order to simplify these expressions. So on number 5 here, for example, I have secant of theta times 1 minus sine squared theta. So if I rewrite these things in terms of cosine, well, that's easy to do with secant. Secant is 1 over cosine theta. Now 1 minus sine squared, I see that sine squared and it gets me thinking. So I go back to my Pythagorean identities and I see, oh, cosine squared plus sine squared equals 1. Well, if I rewrite that and solve it for cosine squared theta is equal to 1 minus sine squared theta. Do you see how I came up with that by subtracting this over? So going back to here, 1 minus sine squared theta. Well, I know from what I just figured out that that's equivalent to cosine squared theta. So now my problem just becomes cosine squared theta over cosine theta, which just simplifies to cosine theta. This is just like having x squared over x. It would simplify. You would cancel out an x, and you would just have the x left. You can do the same thing with your trig ratios. So all of this up here in number 5 simplifies to just cosine of theta. So I want you to pause the video again, and I want you to simplify number 6 by trying to write everything in terms of cosine if possible. So here on number 6, you cannot rewrite sine of theta because it already is a fundamental trig identity. It cannot be rewritten. Cosine theta is already written in terms of cosine. Tangent I rewrote as sine over cosine, plus cotangent I rewrote as cosine over sine. So now I've got these two fractions over here, and then I have sine and cosine out in front wanting to be multiplied by these fractions. So you have two ways that you could approach it. You could have tried to get a common denominator and add these fractions together before worrying about what was outside. That's not what I did, but you could have done it that way. It just would have taken you a few more steps than it took me to get to my final answer of 1. What I chose to do was to take the two terms that were outside and go ahead and multiply them through. When you multiply sine of theta and cosine of theta times this first fraction, your cosines are going to cancel, and then you just have sine of theta times sine of theta, which becomes sine squared theta. And then in the second fraction, your sine values will cancel, and so you have cosine times cosine, which is cosine squared. So then you just have a Pythagorean identity of sine squared theta plus cosine squared theta, which is 1. So all of this mess up here in number 6 just simplifies to 1. So now let's try some more simplifying, but in terms of sine, trying to rewrite things in terms of sine. So on number 7 here, I have cosine squared theta over 1 minus sine of theta. So if I'm trying to rewrite things in terms of sine, I know that cosine squared is 1 minus sine squared theta over 1 minus sine. Okay, now all of you people who want to right now cancel out the 1s and cancel out a sine and say my final answer is sine of theta, you are wrong. This is actually requiring some factoring. So let's work over here. What if I'd had 1 minus x squared over 1 minus x? 1 minus x squared would factor to 1 plus x times 1 minus x, because it's a difference of two squares. Remember that? So then the 1 minus x's would cancel, and I would just have 1 plus x. So how does that translate back to what I've been doing here in number 7? Well, x's are just variables, just like sine of theta is really just a variable. So it can be dealt with the same way. So 1 minus sine squared theta could be rewritten as 1 plus sine theta times 1 minus sine theta as a difference of two squares. And then over 1 minus sine theta. So now your 1 minus sine thetas will cancel, and you're just left with 1 plus the sine of theta. So cosine squared theta over 1 minus sine theta is equal to 1 plus sine of theta. Aren't these fun? I love trig identities. They're like a little puzzle. Alright, so now number 8. And I will go ahead and warn you that number 8 is going to make you feel like you're going around in circles. But give it a try. See how you could maybe go about simplifying it by trying to rewrite it in terms of sine. Alright, so are you going around in circles wondering what in the world you're really supposed to be simplifying this to? I started the problem off by rewriting cotangent squared as cosine squared over sine squared. And then I thought to myself, well, I'm supposed to be trying everything in terms of sine. So how about I rewrite cosine squared as 1 minus sine squared? And then I thought to myself, well, okay, but that still looks like I could probably do something with it. So since I only had one term in my denominator, I decided to split the two pieces of my numerator into separate fractions. I wrote it as 1 over sine squared minus sine squared over sine squared. So then 1 over sine squared is just cosecant squared, and sine squared over sine squared is equal to 1. Now let me be honest with you. Number 8, I kind of feel like that's not a very good problem for them to ask you to really try to do anything with. So if it was a test or a quiz, you would probably see problems like 5, 6, or 7 in terms of simplifying, but I doubt that I would give you a problem like number 8 unless it was multiple choice and then you had to pick something that cotangent squared could turn into from the multiple choice options. So don't be stressing out about number 8. 5, 6, and 7 you should be able to do on your own. So now let's actually try a word problem. This is something that you could use in physics, talking about resistance and a coefficient of friction. You'll learn all about this in physics. It says an object on an incline will start to move when the weight component is equal to the resistive force of friction. So if you have something on an angle, whatever that object is not going to start to slide down the incline until the weight component is equal to the resistive force of friction. And the formula for the weight component is mg times sine theta, which is mass times the acceleration due to gravity times sine theta. And the resistive force of friction is mu, that's a mu, not a u, a mu, times mg cosine theta. Mu is the coefficient of friction. So number 9 says, at what angle with a wooden block on a concrete incline start to move if the coefficient of friction is 0.62? So remember, the key component is that in order to be able to move, the weight component, mg sine theta, has to equal the resistive force of friction, mu mg cosine theta. Now look at this equation here. Before I even worry about the coefficient of friction, do you notice how both sides of the equation have an m and a g on them? So they're going to cancel out. So really this problem is just that sine of theta has to equal mu times the cosine of theta. Now I can use the fact that mu is 0.62. And remember, my whole problem is to figure out the angle of incline that I need my concrete incline to be built at in order for the block to start to slide. So I'm trying to solve for theta. Well, right now I see two terms that have thetas in them. So I need to get those combined together somehow. And I would not move the 0.62 because it's fine where it is. So if I take cosine and divide it over here, I have sine of theta divided by cosine of theta equals 0.62. Well, from my trig identities, I know that sine over cosine is just tangent of theta is 0.62. Well, okay, if tangent of theta is 0.62, how could I find theta? Hopefully you're already thinking, oh, inverse tangent, inverse tangent. So if I do the inverse tangent of 0.62 in my calculator, that'll tell me what angle I need to build my incline at. Now, make sure that you check what mode your calculator is in. It does not specify how it wants the answer for this problem, so I would take it either way. If you put it in degrees, you should have gotten 31.8 degrees, or if your calculator is in radians, you would have gotten 0.55 radians. Most of us would probably think about 31.8 degrees just because those are measurements we're familiar with and we can kind of picture an angle that's 31.8 degrees.